Welcome to Finite Element Methods. Today we'll be discussing springs, which is we're going to be first starting with the equilibrium approach. There's also the energy approach. We're covering both of those methods separately. And then we'll be looking at some application examples. Just to remind you, finite elements is a method that allows you to solve partial differential equations in an approximate way. And it can be applied to a lot of different fields. And it works by discretizing the domain into small domains for which you can approximate the solution over the small domain, and then you can assemble the whole thing together and form a linear or algebraic set of equations that can be solved for. The basis for finite elements. The basis for finite elements is approximation theory. But before I step into that, we will introduce a simpler mathematical idealization, and that's springs. Now, in the book, we start discussing approximation theory right away, but we're going to teach it a little bit differently because it makes more sense when you actually teach it. But for a book, it makes more sense to have it in the order we have it. So why are springs useful? Well, you can create simple idealizations of a structure. So say I have an example of a 1D structure with aluminum and steel. I can apply a load P, and that load P is going to expand this structure, extended, and the aluminum and steel will both get extended. This can be idealized, and what I mean with idealized, right? These are 3D structure. The aluminum is a 3D structure. The steel is a 3D structure. But I can apply a load and expand it. And so that this piece right here can be represented instead as a spring, because the spring can also stretch. And for aluminum, we've taken that and chosen one single spring element, and that's a label here. This exponent here is not an exponent, it's a superscript indicating that this is element number 1. We've taken the steel and idealized that as a spring as well, with a superscript 2, indicating that this is a spring for element 2 that's representing this steel. Now, because I have a spring now, the spring has 2 connecting ends, a node on either side. Because when you have a spring, it has the end of the spring has 2 points. So on one point I can fix it. On the other point I can measure how much it deflected because it's between the aluminum and steel. On the other side of the steel, I have the end of that second element, and I apply a load P there. Now in real life, every single point here can deform, can move, every point here. But in the spring model, I can only track this node, and this node. So these are 2 elements here. Each element has 2 nodes, you can see that here. But I can only track, the deflection here is 0, of course, is fixed, but these are the only ones that can move. This is a degree of freedom, that's a degree of freedom, and this is D1 and D2. And if I can solve for D1 and D2, perhaps I can find an approximate solution to how this structure at the top deforms. And so that's what I mean with idealization. This spring obviously is not the same thing as this, because in real life, this is going to have some Poisson effect. So if I apply a load P, this expands and the lateral sections contract. And clearly, this is representative of an idealization of that structure. And so the spring cannot contract in that direction, it can only extend. That's what springs do. So obviously this is an idealization, but it can be very good approximation. So what is a basic FEA procedure is to discretize the continuous body, and that's a continuous body here, into elements. And what I mean with elements is subdomains. I took this aluminum and represented that as a single spring, so that's one domain. I took the steel, represented that as another element, that's another domain. We can approximate the local behavior of elements in terms of discrete degrees of freedom. We can then patch together or assemble the elements together to form a global system of algebraic equations, and then solve for the discrete degrees of freedom. So let's first discuss the discretization process. So let's look at this. I have the actual structure, which is aluminum and steel. And so what I'm going to do, I'm going to discretize it with one element here. So that's element number one, that spring is going to be representative of this actual, this bar that can be actually deflected. This bar cannot take any lateral loads, just axial loading. So that's why spring makes sense, because a spring extends just like this bar, 3D bar. So that's element number one. For the steel, we're going to use element number two. And what you see here is that element number one has two nodes, one and two. Element number two has two nodes, one here and one here. Globally speaking, you have that this is node number one, node number two, and node number three. And this is element number one, element number two, and you can see here that this degree of freedom, I'm calling this the degree of freedom because that deflection is a degree of freedom here in this case. D sub zero, I have three of them, D sub zero, D sub one, and D sub two, and they're at the nodes, right? On the left-hand side, I have a load Q and a load Q2 here and a Q1 in the middle. So those are the locations where I can apply load, and at the locations where the nodes exist, I can apply deflection boundary conditions. So I've discretized the body into two elements. I've described what this means. You can see here that a stiffness property has been assigned to this spring for aluminum, and a stiffness property was assigned to the steel as an example. So I'm calling the Q's here the global nodal applied loads, and DI as a global D1, D2, and D sub 0 as a global nodal deflections. So I've already explained how to discretize and idealize this structure into springs. Now let's study how to approximate the local behavior of elements in terms of discrete degrees of freedom. So when I look at a single element, let's just select just one typical element here. Just one element, could be this one or that one, I don't care. Let's just look at one of them. And I'm using variables here, so don't get all worried. But the way this works, Finite works, is to understand how to approximate the behavior over a single element, and then take that behavior and apply to every element that looks the same, and then assemble the whole thing together by connecting them. So here I have a spring element. That spring element has two nodes. I'm going to label this node as I and this node as J. The E here represents the element number. It can be anything you want. That's something you make up. It could be 50,000, 1001, whatever you want. And the node number is also arbitrarily selected, but you don't want to have the same element and node number across the whole model. It can get confusing. So these are unique identifiers, I and J. This spring has two nodes, I and J. I have a force here that could be applied or is internal to the spring. So that I'm going to call Fi, and that force is at node I. That's what that's saying. And then force is at node J here at this node. And then you have these deflections that could be occurring at this point and at this point that I'm calling Di and Dj. Again, the superscript here is a label representing, hey, these quantities here are for element number whatever you want to make, 10,000, whatever you want to make it. But I want to understand the behavior of this spring over this domain, this single element. So when I look at local equilibrium, if I sum forces in the x direction using Newton's law, this force plus that force equals 0. That's a local equilibrium. That makes sense. So therefore, one of the forces is the negative of the other. That makes sense also. And since this is equal to this force, then they're also equal to F, to some value F that I don't know. And now when I apply Hooke's law, I think everybody here knows that the spring constant and the force and the deflections can be related. So if this deflects an amount Di and this deflects an amount Dj, the relative deflection is Dj minus Di. And we know that K times the relative deflection of this spring gives you the force that you have in that spring. And so that's what we have here. K times delta L equals F. You've seen this before for a spring. K is a spring constant, F is a force in the spring, and delta L is the stretching that you may have. But we know that delta L, the relative deflection, is dj minus di. So here we have three equations: the local equilibrium, Hooke's law, or the constitutive law for spring, which is K times the delta deflection, dj minus di, equals the force in the spring. And obviously the change in the deflection delta L, not the deflection, but the delta L, the relative deflection between this point and this point is clearly dj minus di. That is it, okay? So here is a local element. So in the local element coordinate system, we're looking at a local element. We're not looking at all the elements at the same time, just a single element. For a single element, the nodes are going to be 1 and 2 typically. You're going to see when you see books deriving this, my own book even. But here I'm using I and j. And that's a local identifier. Every element can have an I and j of its own. But when you assemble the whole thing together globally, every node will have a unique identifier. So when I put everything together, you notice that I can plug this equation in here and I get K times dj minus di equals F. But F can be either this or that. So I have really two equations if you think about it, which I can put in matrix format. You can see here, what is matrices, by the way? When you multiply matrix times a vector of displacements equals force, what does that exactly mean? When you see something like that, don't panic. This is simply saying that I have two equations. So I can take the first row, 1 minus 1, k, 1 minus 1, and multiply by the column, and that gives me this force. So that's the first equation. And then I can take the second row, multiply by the column, and I get the second equation. So that's this representation is just two equations. There's nothing more to it. I call this the element stiffness matrix, and that's discussed in my book. This is the deflection vector for that particular element. And this element, again, has 2 degrees of freedom, di and dj. And so that's what that represents. And then I have the force vector that's going to give me, that I have, and that's basically here, this fi and this fj. And I've drawn this here, I've written that here. And you will see that if you multiply this row by this column, you get that force. And when you multiply this row by this column, you get that force. You will get these two equations. And so every single element is going to have this representation. The element stiffness matrix, listen to my words, the local element stiffness matrix, local, we're deriving it for single element, the master element. Every other element is going to try to follow that. And we're going to try to derive as generic as we can. This column vector is D, this column vector is F. Again, K is the element local stiffness matrix, D is a local displacement vector, and F is a local force vector. So now that I have approximated the local behavior of the elements for a single element, now I want to figure out a way of patching together everything together, assemble it together to form a global system of algebraic equations and to be able to solve at a discrete degrees of freedom. So in our example problem, if you recall, we had two elements. I took this structure and subdivided that into two elements. So for element number 1, I have this with a stiffness, spring stiffness there, that's representative of aluminum. And here I have K, element number 2. But you can see the element stiffness matrix, the local element stiffness matrix equations don't change. They're the same. The only thing changing is the spring constant changed. And that spring constant is selected to mimic the behavior of that material. Clearly here you can see I have a superscript 1 that represents element number 1, superscript 2 that represents element number 2. So I had to find a way of patching elements together, connect them at global nodes. I have to find a way of taking these two elements that are separated and putting them together. For the first spring, I have this. For the second spring, I have this. And I want you to notice how these deflections are in this local element representation, I and J. And this is also in the second element, I and J for the second element. And I want to find a way of putting everything together. Well, you can notice very quickly that DI1 for this node is D naught in the global coordinates, in the global system. And so I'm going to replace DI1 with D naught. This was DJ1, but that in the global system is D1. And I'll put that here. For this second element, this used to be DI2, because this element here now has nodes I and J here, and this deflection is DI2, and this is DJ2. You can see them here. But I need to relate that to the global system. So that becomes D1. And for this last degree of freedom, I have DJ2. That global degree of freedom deflection is D2. And so now I have these elements representing in the global orientation system. I've related the local to the global. Okay, so now what I'm going to do, I'm going to do a little trick. I'm going to try to look at forces now. And before I do that, let's look at what's going on globally. I have a spring here, spring here. I could have a force applied externally here, Q0, Q1, and Q2. But I want to look internal. I want to do a little cut here, a little cut here, a little cut here, a little cut here, and see what's going on there internally. So when I do a little cut here, what I have is that at that node, I have Q0 applied, but a force has to be reacting that. So I'm calling that Fi1. And these two forces have to be in equilibrium with each other to get zero. This is an internal force. So that has to go to zero here and has to somehow add up to Q0. When I do a cut here, I get that's FJ1, that's element number 1. And remember, I is the nodal label. Don't get confused. It could be 1, 2, whatever you want. But I called it I so we don't confuse it with this 1. For element 1, that node is I, and that node is J. And so what I've done is showing that element, I cut it here, and internally, that force internally has to be in equilibrium. Fj1 has to be equal and opposite from this force, Fj1. When I do a cut here, or looking at this node itself, I have this force, I have this node, I have this external load applied, Q1, to that node, but I also have this force coming here that comes from here, from this cut. I do the cut there, and I see that force here is equal and opposite again, Fi and Fi. Node I from element 2, right? Because element 2 has that node I and node J. And again, same thing. And then when I come here, I do a cut there, and again, I have Fj for element number 2, node J. It should be equal and opposite, and should be equal to somehow the force externally, Q2. So I'll sum now forces in the x direction. So I get Fi1 equals Q0, has to be at that node. Then I continue here at this node, I have this force plus this force equals Q1. And at this node, I have this force equals Q2. Okay. So I've done equilibrium now. That's the first equation for element number 1. That's the second equation for element number 1 and first equation for element number 2. That's how we combine these two to get to that one. That's what happened there. And then I have the second equation for element number 2. So that's what we have. We have these 3 equations here. And what I want to do is I have these 2 local element stiffness matrices, this for spring 1, this for spring 2. I want to take this information, and basically what I want to do is to combine them somehow. And the most logical way to combine them is to write the equations out. First of all, let's just write them out, multiply the first row by that column, and I get this for each of this. Let's do that. So for element number 1, this row times this column is K1 D naught minus K1 times D1, right? So this times that minus this times that equals F1 and so forth. I can do that for every single one of them. Now what I want to notice is I can now combine, I can do a little trick and tell me if you agree. The degrees of freedom that I don't know is D naught and D1 and D2. What I can do is I can expand this matrix in a fake way for the first spring. For the first spring, what I did, I added zeros and zeros and I put zero there. And why that this works, if I multiply that first row by this column, D0 multiplies D2 and it doesn't show up in the first equation, which is exactly what I have here. I don't have D2 here in this equation. So it's working out by adding that fake zero column and zero row. Here, when I multiply this row times that column, again, 0 times D2 disappears, and that second equation doesn't have D2, which is exactly what you see here. You don't see D2. So this representation so far is representative of these two equations, clearly. And I put 0 there because 0 times D2 is 0. There's nothing going on there. For the second equation, I'm going to do now the same thing. I'm going to put a column here of zeros and a row of zeros because D naught does not show up in element number 2 at all. D0, you can see here, element number 2 does not have D0 here at all. So I'm adding D0 fakely, and you can see that here, 0 here, 0 there. And that's great. So what I'm going to do now, that's for element number 1 and for element number 2. What I'm going to do, I'm going to add these local stiffness, these matrix equations, these local element matrix equations for spring 1 and the local matrix equation for spring 2. I'm going to add them together. And you can linearly add them because D naught, D1, and D2, you can see here, that's common between the two. So you can just add the 1 plus 0 is 1, minus 1 plus 0 is 0, minus 1, and so forth. 1 plus 1 is 2, and so forth. I can add it. I can go ahead and add that here, like that. I said 1 plus 0 is 1. I should have said K1 times 1 plus K2 times 0 is K1, and so forth. K1 times 1 plus K2 times 1 is K1 plus K2, for example. So yeah, I have to do that. I have no choice. And that's the way you add them. So this column here is D naught, D1, D2. Great. I can add this force plus 0. That's Fi1, sure. But I already stated earlier that Fi1 for element number 1 is Q naught. We derived this earlier using Newton's law. We also discussed that if J1 plus Fi2 is Q1. And finally, Fj2 equals Q2. So I have a column Q naught, Q1, and Q2. And this is the global. Now, look at this. These are global equilibrium equations. Everything now is in terms of global nodal quantities. I went from local to global. And we've able to assemble, we assembled the two springs together in a way that was sensical using physics. And now this is called the global stiffness matrix. This is a global deflection vector, and this is a global force vector. What you see here is these are the unknowns for the system, and K is a stiffness matrix for the system assembled together. So the question is, given the forces Q naught, Q1, and Q2, find a solution for D naught, D1, and D2. The natural reaction is to invert this matrix to find D naught, D1, and D2. MATLAB or Mathematica can do it, and my book shows it how to do it with MATLAB. The solution to this only exists if this matrix can be inverted. That's the only way this could happen. It turns out that if the determinant of a matrix is 0, you can't really invert it. So the inverse of a square matrix is defined as A inverse times A equals identity matrix, or A times the A inverse of that matrix is inverse. And you can determine A inverse explicitly by calculating the adjoint of A divided by the determinant of A. And you can see here, determinant of A is 0, A inverse blows up. And so it turns out that this matrix K is actually not invertible. If you find the determinant of this matrix, it's going to give you 0. And you can check it yourself fairly quick. I don't want to do it here, but you'll find that that's the case. Actually, I did it here. I apologize. I did it here. When you find the determinant of K, you get 0. And why is that? Physically, why is the case? In the case, the reason for that is that you have rigid body motions right now. Right now, I haven't fixed any of the deflections of that spring. So if I apply a load, the spring will go flying, right? And so in that example, the determinant of K is 0, and you get rigid body motions instead. And so you will see very often in finite elements that if I don't specify enough degrees of freedom fixed, the structure will go flying. It's not adequately restrained. And you can see that here, the simulation of that occurring here in my PowerPoint. It's kind of hilarious to actually watch it. Okay. So in our example now, we don't have a scenario where, I mean, we have is restrained on the left hand side. And so on the left hand side, I know that D naught is 0. So I can impose that boundary condition. I'm calling that a boundary condition. And that global degree of freedom now is restrained. So I put D naught equals 0, and now it's fixed. So D naught is specified here is 0, but we can keep it general. I could have specified a deflection D naught of 1, for example, or 2. So if D naught was specified, you need to move D naught to the right-hand side of the equation. Somehow you have to move that to the right-hand side of the equation. And that's a typical procedure that needs to be followed in finite elements. Anything that's restrained needs to be somehow moved to the right-hand side of the equation. So the first equation, D naught, we know D naught, the value of D naught. In this case, is 0, but it could be having 1 inch, half inch, whatever. But I have here 3 equations. That's the bottom line. 3 equations. And if I look at the second equation, that second equation here, you can see that I have minus K1 times D naught plus this component times D1 minus K2 times D2 equals Q1. That third equation sorry, I apologize. I know D naught. I know the value of D naught. So I need to move this D naught to the other side of the equation, which you can see that was done here. And that was done for the second equation. For the third equation, you have Q, 0 times D naught does nothing. So you're left with just this. And you can see how now the equations are, the only unknowns now are really D1 and D2, if I look at this. D naught is known, the forces are known. So it should be fairly simple to put everything into matrix format like this. All I've done is put these 2 equations here into matrix format. Now I know D naught because it was specified. I just told you that. So that can happen. You could have a situation where D naught is specified. Q1 and Q2 are the global loads applied. D1 and D2 are the deflections are unknown. And the deflections I'm talking about here is this one here, D1 and D2. So now K is invertible actually. You can invert K and solve for D, bold. Now, how to do this more generally, like in a finite element model where there's millions of degrees of freedom, there's a procedure that needs to be followed. So what you need to do is you're gonna have a global stiffness matrix that's millions of degrees of freedom or more, and you have to partition that. You're gonna partition in 4 pieces. The 4 pieces are an upper quadrant of a submatrix, another submatrix, another submatrix, another submatrix. Anything that has a bar in this column vector are deflections or quantities that were specified that you know what the values are. U bold are the ones that we don't know anything about. Q bold is not known, and Q bold bar is known. So we need to somehow make this so that the only unknowns are U bold here. So this column vector is going to have millions of degrees of freedom. We divided that vector into specified and the unknowns. So these ones are known again. This whole stiffness matrix is known, just like this one. These stiffnesses you will know. These are values from the idealization process. The forces are known. Okay, um, and so we had to figure out a way of turning this into something that's useful. So if we multiply the second equation times the second equation, the second row times the first column, I get this. So Q U U bar times U bar. This is fully known as a submatrix. U bar is known. I know every deflection specified there. Plus KUU times U equals Q bar, and Q bar are the forces that are known. So I can now invert this stiffness matrix. I'm sorry, I can invert KUU. So I bring this to the other side of the equation, invert KUU. So I get U bold is this. And so now I'm ready to do some damage. The first equation is QUU bar times U bar plus QU bar U times U bold. This one here. So I don't know this one. I don't know this one. So we have to figure out a way how to deal with that. Q is not known. This Q is not known. Because anytime you specify something, you don't know this one. If you specify this, you don't know this one. So it's either one or the other, you know. So yeah, so that's how it works. Once you know U bold bar, you know this stiffness matrix, you know Q bold bar, you know that one because that's the laws applied. And then you know K inverse completely. So you can calculate the deflections of unknowns. And once you know the deflections of unknowns, you can plug it in here into this equation to find the reaction forces Q bar, Q bold here, the one that you see here. In review, we discretize the body, idealizing the system into whatever domain you think is the best. Here we select the springs, and then we basically figure out a way of approximating the behavior of how an element behaves for a spring. We felt spring was a good approximation because we're we're extending each of these pieces, and springs do a good job of replicating and mimicking that behavior. So this element behavior was derived using Hooke's law, Newton's law, and deflection compatibility. And we showed that for a local element, this node I, this node j, that we can come up with the matrix equation for that local element. And that we can then assemble the springs together using the approach that I taught. And once you do that, you can then impose the boundary conditions to the problem. In this case, D naught was known, it was 0. So once you put that 0, you can now solve for D1 and D2 using the last two equations. And what is very interesting here is that you have this idea of the local stiffness that's of interest to us. And the idea is that a force applied on a degree of freedom J per unit displacement of degree of freedom I is also equal to the force on the degree of freedom I per unit deflection in degree of freedom J. It's an interesting idea. And all that's saying is that the stiffness matrix for linear systems, anytime you have a stiffness matrix, is going to be symmetric. And that's a big help in computational expense in terms of solving problems. And that idea can be studied more, but just wanted to give you that big picture perspective that um, you can, there's symmetry involved, and there's a physical meaning to it, and that physical meaning is force on the degree of freedom J per unit deflection on degree of freedom I, and that's something that you can actually check here when you do it. For example, if I apply a unit deflection here, so I put 1 here and 0 here, you will see that K will become, so again, I put 0 here and 1 here. You will see that I'll get, for that force, I'll get minus K 1, 2 here. And I'll get K2, 2 here, for example, for that second one. So it works out very nicely that the force becomes a spring when you apply a unit deflection. But the bottom line that we wanted to make here not to confuse anybody, is that the stiffness metrics tend to be symmetric because of that for linear systems. And if I look at a local stiffness, you can also label it this manner to help you out, INJ, INJ. And the force vector can also be put in like that, INJ, for simplicity. So a local element stiffness matrix, the matrix equations are going to look like this. Local non-numbers INJ, element number E stiffness K, forces applied at each of these nodes with deflections applied on INJ. So there's another way to go about this, and that's called the direct stiffness method. So let's look at this. You can see here another look at this global stiffness. This is what we got. That's degree of freedom 1, degree of freedom 2. That's equation 1, equation 2. And you can see that degrees of freedom and equation numbers correspond to columns and rows. And because of that, and we discussed how summation of forces leads to summation of stiffnesses, we can do this procedure that I explained earlier, like this whole thing, with all this equilibrium stuff and all this complication we discussed. We can actually do that without doing equilibrium, because now that you understand it, we will find a different way of doing it. And we can do this directly using a local global degree of freedom number map. Let me explain how that works. So, and that's explain my book very extensively and the code on how to implement it in MATLAB or Mathematica. We can obtain the result by systematically assembling the procedure using code numbers. So let's talk about that. So here I have no degree of freedom, so there's no equation number for that. Here I have a degree of freedom number 1. And then here I have a degree of freedom number 2. And so I have, again, degree of freedom 1 and 2. I have no degree of freedom here in D naught because this end I'm specifying the deflection. And note how the deflections and the forces have the same subscript. 1 for degree of freedom 1, 2 for degree of freedom 2. So now what I'm going to do, I'm going to try to relate the local node number to the global node number. In the local element system, this element has nodal numbers I and j. So I'm going to write I and j here. Global node numbers are 0 and 1. If I were to relate I and j, I can relate it to 0 and 1 globally speaking. So I put 0 and 1. For element 2, that has local node numbers I and j. Globally, I'm talking about 1 and 2. So I'll write it down. And you can see that this one I put a 0 because that's a specified value. So now I'm going to write something called a code number. Element 1 has a code number 0, 1, and element 2 has a code number 1, 2. So I'm relating local node number to global node number. That's what I'm doing. All I've done is transfer these numbers here in the first row and these numbers in the second row. So now I will line up the code numbers with the rows and columns of each local stiffness matrix. I have 0, 1, 0, 1 for element 1. You can see that there. For element 2, I'll write 1 and 2 here, 1 and 2 here. But for the global stiffness matrix, I only have 2 degrees of freedom in this system because I fixed this point. So I only have 2 degrees of freedom that are not known. These 2 deflections are not known. So the global stiffness matrix should be 2 by 2. And the degrees of freedom are 1 and 2 and 1 and 2. So what I'll do now, I'll assemble it. For example, if I look at this one here, I can search for location 1, 1. You can see that 1, 1 shows up here. So that one should go here. I search here and I find that 1, 1 is here. When I search it, that should go here. Okay. And so I'll keep searching. I'll keep searching for, now I'll search for this one here. That's 2, 1, location 2, 1. So here I don't see any 2s in element number 1. In element number 2, I see a 2, 1 there. So that goes there. And then for 2, 2, for example, I don't see any 2, 2s in element number 1, but I do see it here. So that goes here. And so forth. You're basically doing a search and adding them up as you go. The only one that had something that needed to be added was this one, because 1, 1 shows up here and here. So those two need to be put in here so they get added up. So that's the quick approach to doing this. Very useful. I have used magic, PowerPoint magic, to show you what it looks like. We have disappeared the black boxes to show you that this is the global stiffness matrix we get. So in example 1, I have this system with 3 springs. I have a spring here, spring here, spring here. It's fixed here. So the only nodal deflections that are unknown are this one. And because this is rigid, I'll say that is this one as well. So I only have 2 degrees of freedom here, but 3 springs and a load applied P here. And this end is fixed. So I can create the code number. Let me clean this up so you can see what we're saying. So for spring number 1, that's spring number 1. I can label things. So this is 0, this is 1, and this is 2 in terms of global degrees of freedom, because this deflection is the same as this one. So for element number 1, which is this one right here, you can see that's connecting 0 and 2. So that's what you see there. Element number 2 is connecting 0 and 1. You can see that there. And then element number 3, which is this one here, is connecting 1 and 2, which you see there. So I've related now the local degree of freedom to the global degree of freedom. Recall that this is I and J, and for spring, the local node number is I and J. So I related successfully to the global system. So the global degrees of freedom, the only unknowns to the problem are D1 and D2. Of course, you can see that here. And now I'll go ahead and start assembling everything. So I take the code numbers 0 and 2 for element number 1 and put them here in this manner. For element number 2, I put them here, 0 and 1. I'm doing that one. Element number 3, I'm putting 1 and 2, following that code number. And now I know the matrix is going to be 2 by 2 because I only have 2 unknowns. I have D1 and D2. Those are the only ones I don't know. So I will go ahead and put everything together. You can see here that the degrees of freedom are 1 and 2 in the global coordinate system, in the global numbering system, not coordinate system, I apologize. So for 1, 1, I do a search. For element number 1, I don't see a 1, 1. In element number 2, I do see a 1, 1 there. So K2 should go here. Here in element number 3, I see a 1, 1 there. So that's that one. That should go here, which you can see there. And then I keep going. I keep looking for fitting this up by searching element by element. Whatever I see that component, I'll just add it in there, right? So one more example, we can do 2, 1. 2, 1 does not show up here, does not show up here. I do see it here, and that can go right there, which you see there. You can see that's there, right? And we could do one more just for fun. 2, 2. 2, 2, this right here, that one, which you can see here. And then 2, 2 shows up here, which is that one, and you can see there. So that gets added up. The load, there's no load applied on this node. I don't see a load applied, but I do see a load applied here of P. So now all I have to do to solve for the deflections is to invert So I have K times D equals Q. In a typical problem, K is fully known. The load is known. You apply 1,000 pounds, whatever. You can invert this K now to get D, right? The deflections. Yeah, so I will label it whatever I want. I can make this 0. I made this 1, and I made this 2. That's the global values. So I could have make it 0, 3, and 4 if I wanted to, but then I have to use the same numbers everywhere. It doesn't matter what you assign it. I could assign it, for example, I could assign it to be 0, 4, and 5. Is whatever you want. These are labels only. So for the first element is connecting degrees of freedom 0, 5 for element number 1. For number 2 is connecting 0, 4. For number 3 is connecting 4 and 5. And then later on, and then I have to change these now in the global to call these 4 and 5 from now on instead of 1 and 2. So this is something that you assign, that you may have to assign arbitrarily, but I'm using, consecutive numbers to make it easy. Let's look at this example. I have a structure that looks like this. It looks weird. It's like some sort of hook. And I apply, and maybe that has holes here that are small, but I'll idealize it and not model the holes. And I apply a load P, and so it's distributed P half here, P half there. I have to figure out a way of idealizing this. The cross section is varying. You can see that there. The cross section here is also varying. And the length here um, is, as you saw, L1 and L2 and L3. You can see here that I've discretized the domain into maybe say a little rectangle here, and a rectangle here. So I'm going to idealize it with springs. So I'll take the top portion, put springs, the bottom one as springs, and this little sliver here as another spring. And on this end is D naught. And it turns out that for a bar, the spring stiffness can be represented as EA over L. So the modulus of the material times the cross-sectional area divided by L, where A here obviously is varying, so you have to be smart about what to choose for area. You could choose the average between here and here, for example. So maybe you can choose somewhere in between for that area, because you're idealizing, right? It's an approximation. That's what finite element is. It's an approximation. And you can make some simplified assumptions that you want to do. What is the element code number? So I have 3 elements, 1, 2, and 3. So for this one, element number 1, so now I can then go ahead and start numbering things. So here I have a degree of freedom 0 because it's fixed. Here I have degree of freedom 1 in the global system. And here I have degree of freedom 3 in the global system. Notice I stopped the spring where the load is applied because this section is not going to contribute to any deformation. So that's why we stopped it there. So I'm idealizing this levers here. This one, and this one. Those 3 elements are represented with springs. So because that's one, element number 1 is connected by 0 and 1 because that's degree of freedom 1. So that's what you see there. Element number 2 is connected by 0 and 1 as well. While element number 3 is connected by 1 and 3. No 3. Sorry, no 2. Degree of freedom 2. So I have 1, 2 there. So that's how that works. Very simple, nothing complicated. clean this up. And I'll again explain the procedure really quickly, but I'm interested in doing, say, 1-1. That's an interesting one because look, 1-1 shows up here, it shows up here, and shows up here. So they have to be all added up, as you can see there. That's that one, that one, that one that has to be added up. So you have to basically search for these guys and populate it. In our case, a load, there's no load applied here. There's a load applied on this end, which is P, and I put it there. How can you calculate reaction forces once you have all this information? Say I want to know the reaction forces on this end. Like what is the reaction force there? What you can do is solve for the deflections first. So you solve for these deflections, and then you go to the local element system for element number one, for example. Element number one is this one. I know that this is degree of freedom 0, so that's 0. Globally, this is D1, but locally also is D1 because that node is connected here. And so, but I know D1 now. I know what D1 is. I know K. So I can actually get the forces for that spring here and here, right? From the first equation, get F1, Fi, the load, the reaction force here. From the second equation, you get the load here at this node. Element number two, the same way. That was for element number one. Element number two, the same way. I can calculate the force again for that element. I can figure out what is the force internally there. What is going on there? I can tell you internally what's going on there. That's what we're doing in this step. In summary, we discretize the body, idealizing the body into simple elements. We approximate the local element behavior, and then we assemble the global equilibrium equations using the code number approach that I discussed. And doing that allows you to quickly put everything together in a way that's simple and can be combined.